For example, the moon reflects sunlight. The moon is heated by the sun and gives off thermal emission. The moon can be impacted by various objects, and ejecta can be a hazard to engineering operations. Neutrons are generated in the surface layer by the galactic cosmic rays hitting atoms in the surface layer and changing them to radioactive elements. And the surface itself can acquire electric charges through the interaction with the plasma environment of the solar wind. The moon is in general a dark object, having an albedo of around 7%, although some areas are brighter than that, some areas are a little bit darker than that. If you look at a picture of the moon, you see dark and you see light areas. The dark areas are basaltic lava flows that we called mare, the Latin word for seas. The highlands are the lighter objects, and these are the original surface of the moon before the great bombardments in the early history of the solar system. The reflectance of lunar soils, although they're really quite dark, tend to be slightly reddish, so the albedo or reflectance in the blue is slightly lower than the reflectance in the red and in the near infrared. The reflected light off the surface of the moon shows a surge at zero phase. And what this means is that when we see a full moon where the sun is right behind the earth and shining on the moon, all areas of the moon are at their brightest at this, what we call zero phase. And this reflective property was a puzzle for a number of years, but now we understand better what causes it. The upper millimeter or so of the lunar surface has a very porous structure that causes this very high retroreflection. I mean, retroreflection is a term like highway reflectors. When your headlights show on them, they tend to send the light right back to you. The moon is like that. If we are on the moon and looking down sun, that means the sun is behind our head and we're looking in the opposite direction, we see a loss of detail like you would see, say, on a ski slope where there's a whiteout and you can't make out what features are. This lunar photometric is odd, but it's very well documented and modeled and can be accounted for in engineering operations. The lunar surface is heated by the sun as it rises and sets, and is hottest when the sun is directly overhead. The temperature profile at any point on the moon is periodic. That is, as the sun rises and sets, it follows a particular curve that repeats itself over and over, day after day. When the surface temperature is periodic, the temperature measured at depth will also be periodic. But the shape of the curve with depth will change, and the amplitudes will become less. So that as you go down into the surface, the temperature variations around some sort of mean value get quite small rather quickly. And on the moon, the thermal inertia is quite low, and that means that as you go deeper into the surface, the thermal wave and the temperature wave that you see on the surface becomes muted so that the amplitudes vary only a little bit and as around a medium. So at a meter or so beneath the surface, a temperature probe does not even register the rising and the setting of the sun. The low thermal inertia of the lunar surface means that heat is inefficiently conducted into the interior. So the solar heat is collected at the upper surface, and that surface temperature quickly comes into radiation equilibrium with whatever the sun's input is. Of course, the sun's input is a maximum when it's directly overhead, and that's when the temperatures are the hottest. If there are slopes, the temperatures are the hottest when the sun is shining directly on the slope. So topography will exhibit a range of temperatures at any particular time of the lunar day. The lunar surface has large rocks sitting on it, and smaller rocks for that matter. Rocks, being more solid than the lunar surface, have a much higher thermal inertia, so heat is conducted into the interior of the rock more easily than is the case on the lunar soil. As a result, the rocks will remain cooler during the lunar day, and as the heat comes out of the rock during the lunar night, their surface will remain warmer than the surrounding soil. The galactic cosmic rays and the solar particle events strike the lunar surface with very high energy, and they can cause nuclear reactions with the atoms of the surface material of the moon. The interaction of the high energy particles with the subsurface create temporary radioactive elements which decay and emit neutrons. These neutrons find their way out of the surface and can actually be detected from orbit, and sensors